Hello everyone. So in last class we have discussed the theory part of electric potential, right? So today I'll try to take up some questions from H.C. Verma. So all the models that are based on electric potential, and we'll try to solve and analyze the situations that are given. So these are some standard models which will be given for JEE mains and Neet and BITSAT regularly. So let us go through these questions and let us see how to tackle these type of standard and basic questions. Okay. So in this question, so here they're telling there are two particles A and B having charges so and so. One is positive charge, another one is negative charge. Respectively are held at a separation of 20 centimeters. 20 centimeters means what? 0.2 meters. So let's say imagine we have like 2 point charges like this. We have 2 point charges. So the first one is, let's say, q1, and the second one is what? Let's say it is q2. So here they are asking us to find, so the point where the field will be 0 and the point where the potential is 0, right? So already you guys know the formula for what? Field and potential due to a point charge. Field is what? Kq by r square, and potential is what? Kq by r. Okay, so here I am not going to do the calculation part, but I am just going to explain how you need to approach these type of question, and I'm going to also explain where people will often feel difficulty in approaching like these type of questions. So where people will feel difficulty means, so they'll try to analyze more, and they need to they wanted to know where the potential will be 0. So instead, for doing so, either they'll be guessing or they'll be getting confused that where I should be taking that point, here or here or here. So remember, so in physics, okay, most of the times, or almost all the times, whenever we don't know the side or the direction of anything, so simply we can assume anywhere. And if whatever the assumption we have done, if it is wrong, then that value, magnitude, is not going to change. Simply we are going to get what? Negative of that. So that's why, so you guys shouldn't hesitate, or shouldn't be analyzing more and more in thinking about the direction, what direction you might be getting, or which side you will be having. So wherever you feel it would be okay, wherever you feel that that point will be there, so there you just take it. And whatever the assumption that you have taken, if it is wrong, as I said, that value, you will be getting that value as what? Negative. So I am just doing only for the potential part. So let me take this point. Let's say I consider that at this point the field will be 0. If I take this distance to be x, and this remaining distance will be what? D minus x, because the total distance is given as what? Total distance is given as d. So therefore, simply for the potential at p to be 0, okay, as potential is a scalar quantity, potential due to each one individually, it should be what? 0. That means simply what will you write? So which implies that a potential is a scalar quantity, no need of bothering about direction and all that stuff. In field, you should be bothering about the direction of that force as well, okay, or the field. So here, as it is scalar, simply I'll add kq1 by what? Kq1 by x square plus kq2 by d minus x whole square, which you should be equating it to what? Which you should be equating it to 0. Okay, which you should be equating it to what? 0. So from here, you just substitute the value of q1 and q2. Okay, you should be just substituting the value of q1 and q2, and also the value of d. So value of d is what? 0.2. So from here you will be getting the value of x. If x is a positive, okay, if x is a positive value, that means you need to understand that. So I'll just tell here there are three cases that might arise. So x can be what? So there are three cases that are possible based on the charges. What are the three cases? These are the three cases. What are the three cases that are possible? See, I am trying to analyze the concept, complete concept, okay. So finding the answer of this question is not my intention. So I wanted to explain the concept so that any type of question that is given on this model, you should be able to tackle it, right? So there are three cases that are possible. X is what? X is negative. X is what? X is a positive value, and x is less than d, and x can be greater than d. So these are the three cases that you can get, depending on the value of q1 and q2. So if x is negative, then you will be telling that the potential, the point where the potential will be 0 is what? So here in this region. And if x is less than d, x is a positive value, and if x is less than d, then you will be telling it is in between the charges. If x is more than d, then you're going to tell it is outside this region, right? So from here it's just calculation k, you can just send it out the other side, and q1 and q2 values are given, d is given, just substitute there and we find the value of x. Okay, so this is one standard problem. So I hope it's clear for everyone. So let us move on to the next question. The next question they're telling three identical charges, each having value 1 into 10 power 1 into 10 power of minus 8 coulombs, are placed at the corners of an equilateral triangle of side so and so. Find the electric field and potential at the center of the triangle. Okay, so they're asking us to find the potential at the center. So already similar type of question already I have taken it up, right? So in the theory part, but there I just asked you to find the interaction energy, and I have given a square on the three vertices. I kept the charge and asked you to find what's the potential over here. Now instead of that, so they have given three identical charges over here like q. Now they are asking side length is given. Let's take side length, which is given as 0.2. Side length is given. Now you guys need to find what is the potential at the center, right? So you guys need to find what is the potential at the center. So you know the potential in the center, let's say, let me call this point as O. We want to find the potential at O. So when this length is A, as these angles are like 30, 30 and 120, what will be this angle? Angular bisectors, no? So 30, 30 and this will be 120. So sides will be of ratio what? 1 is to 1 is to root 3. So therefore what will be this length? This length will be A by root 3. And this length will also be what? A by root 3. So this length is A by root 3 and this length is also what? A by root 3. Now I know the distance. Okay, I know the distance from each and every point charge to the point where I need to find the potential. As the point is located in a symmetrical manner for all three charges, and the charges are also what? Equal. So therefore potential at O is nothing but 3 times kq by r. So what is r? R is nothing but A by root 3. R is nothing but what? A by root 3. So therefore from here what's the value you will be getting? So you'll be getting 9. One second, what I have done, my bad. So here the potential 3 times what's the potential due to each charge? Potential due to each charge will be kq by r. R is what? A by root 3. So what will be the answer? So the answer will be V naught equal to 3 root 3 kq by A. So you just need to substitute the values of k. K you know, it's 1 by 4 pi epsilon naught, 9 into 10 power of 9, right? And k value and q value you guys know. Okay, it's given in the question, and A value also you know, right? So just substitute here and you're going to get the value, right? And then let us move on to the next question. So in this question they're telling there is a uniform electric field. Okay, so here this point is important. I'll explain what is a uniform field. So remember, uniform field means, so as we are discussing concepts, I'm writing a concept here. So uniform field means what? Uniform field means both magnitude and direction. Both magnitude must be same magnitude, and also same direction, same magnitude and same direction. For example, sir, how this uniform magnetic field lines will be there? Sir, how this uniform magnetic field lines will be there means parallel lines, which ensures that the direction is like same everywhere. And just being parallel is not enough. Okay, for the magnitude to be same. So this is how the uniform electric field will be there. So this is what? Uniform field. So this is uniform field, I'll say. Okay, later we'll see this will be the same definition for uniform magnetic field as well. So what is the meaning of uniform? Same magnitude and same direction. Sir, how you are telling same direction? Each and every vector is pointing towards right, so direction is fixed. And for the magnitude to be same, here I'm writing for the important thing, for the magnitude to be same, the separation must be fixed. The separation is constant. The separation should remain what? Constant between these field lines. Then only you'll be telling this as what? Uniform electric field. Okay, uniform electric field. And remember, whenever uniform electric field is there, then the relation between electric field and potential is given by this formula. In general, for any case, actually the formula is what? E equal to minus dv bar dv by dr. E equal to what? Minus dv by dr. But in the special case, what is the special case, sir? The special case is if field is uniform, whenever the field is uniform, then remember this formula can be simply written as E equal to minus delta V by delta R. Minus delta V by delta R, I can say delta X. And you need to understand very important thing over here. You need to use this formula only when the field is uniform, and this delta R distance, I am going to highlight this delta R distance. Delta R distance is in the direction of field. The delta R that you should be taking is what? In the direction of field. This is also very important. So later in solving some important models, this will be helpful. Just remembering this formula is not enough, right? You also need to have a clear understanding about like each and every term and how to utilize that term and how to use that term, right? Okay, so this is the concept, right? Okay, now they're telling find the increase in potential energy as one goes up through a distance of what? 50 centimeters. 50 centimeters means 0.5 meters. So first of all, they are telling that how the field lines are there. Uniform field lines vertically downward, right? Exist in vertically downward direction. This is how the field lines are there. So remember, already in the theory part I told, field lines will always flow from where to where? Higher potential to lower potential. Higher potential to lower potential. So that means, so the upper side, so the upper region will be of the higher potential. This is the higher potential region, and this is the what? Lower potential region, right? So this is the higher potential region and this is the lower potential region. Fine. Now they are asking when we go up by a distance of what? Go up. That means in the direction means basically you can take like along. So basically instead of telling in the direction of field, I should be telling along the direction of field. Why? Because sometimes you can travel in the opposite direction of the field also, right? So that's why I'm writing. I'm changing here. So I need to write along the field. Okay, along the field. That means along the direction of the field. It can be either in same direction or opposite direction. So as I said here, the upper region is higher potential region and the lower region is lower potential region. When I go from here to here, obviously the potential will increase. The potential would be what? Increasing. So here that's what they have clearly mentioned. That's what they're asking. They're asking find the increase in potential. So how to find the potential? So coming to the like just the magnitude part. Okay, so I just want to bother about the magnitude. Here negative sign indicates that electric field. So what does that negative sign indicates? You know, the negative sign indicates that the electric field will always flow from higher potential to lower potential, sir. How the negative sign indicates means in physics, remember delta means what? Change means always final minus initial. And what is the meaning of dv? Dv is nothing but delta v tends to 0. The change only when the change is very small, then we'll call it as dv. Okay, the delta V tends to 0 will become what? dV. So as I said, electric field lines will flow from higher potential to lower potential. As I said, electric field will flow from higher potential to lower potential. So obviously in the direction of field, the potential will be decreased. So when I do final minus initial, we will be getting a negative value, right? To compensate that negative value or to give an explanation that the electric field will be from higher potential to lower potential, we need to keep a negative sign over here. So if I just want magnitude, I won't be bothering about this negative sign because already I know that field will flow from higher potential to lower potential. So if I just want magnitude, so simply I'll take it as what? E equal to mod delta V potential by mod delta R simply. Magnitude I am writing. So therefore from here the potential difference delta V magnitude is nothing but what? Delta V magnitude is nothing but simply E multiplied by delta R. What is the value of E? This is the value of E and this is 0.5. So therefore answer is what? Answer is 5 volt. So therefore there will be increase of 5 volts when we are moving in what direction? When we are moving in upward direction. Similarly when we are going in downward direction, the potential will decrease. Okay, why? Because the field is going in the downward direction, so field will always flow in the direction of what? Decrease in potential. So if you go in the upward direction, the potential will increase. If you go in the downward direction, the potential will decrease. Okay, so I hope it's clear. It is an important concept, okay, and very standard and favorite concepts for the competitive exams as well. Uniform electric field. Yeah, fine. And next question is, 12 joules of work has to be done against an existing electric field. So they are telling this much amount of work should be done. Okay, that means this is the work done by the external force. Here also I'm going to tell one more important concept. Okay, so try to listen carefully. An existing electric field and charge is given for, it's taken from A to B. It's taken from A to B. That means A is the initial and B is the final. Okay, A is the what? So initially it is at A. This is initial point, and B is what? B is the final point. So you guys need to understand initial point and final point. So this is initial and this is final. Now, so here I am going to tell one more important concept which will be very much helpful in solving questions. So in dipole, in magnetic moment, so everywhere in all these concepts, all these chapters, it is pretty much useful. Work done by external force. Work done by external force is nothing but what, work done by external force is nothing but change in potential energy. Change in potential energy delta U. But if I ask you what is the what is the electric work done by the electric force, work done by the electric force is nothing but minus change in potential energy. That means delta U means what? Final potential energy minus initial potential energy. So minus delta U means what? Initial potential energy minus final potential energy. So in yesterday's theory part already, as I've given the formula for the relation between U and V, that means potential energy and potential energy and potential. That is potential is nothing but potential energy per unit charge, right? So therefore by manipulating here, so if I just take charge Q outside, I can write final potential minus initial potential, and here I will be writing Q into initial potential minus final potential. So it is very, very, very important that you guys need to understand that work done by external force is change in potential energy, but work done by the electric force is what? Minus delta U, minus change in potential energy. Okay, very, very important. As I said, it will be helpful in dipole. Okay, it will be helpful in dipole. It will be helpful in magnetism chapter, that is magnetic moment and bar magnets concept. Okay, so there also it's pretty much helpful. There, instead of having work done by the electric force, they will be having work done by the magnetic force. Fine, sir, we understood. Then, sir, how to approach for this one? It's simply done, right? It's taken from where to where? A to B. They're asking how much. So they already given work done by external force. Work done by external force is given as what? 12. So therefore 12 equal to Q multiplied by, so see, work done by external force is given, which is nothing but Q multiplied by final potential minus initial potential. When it is taken from A to B, okay, A to B, so which will be the final potential? This is the final potential and this is the initial potential. So therefore what I will be writing? VB minus VA. So, and Q value is already given. Q value is given as 0.01. So therefore the value of VB minus VA, so you should be very careful with the sign, initial point and final point. Why? Because in the options you will be having both positive values as negative values. Okay, even if you miss the concept a bit, okay, so if you are having misconception with this negative sign and all this stuff, so then you're going to opt the wrong option and you will lose your marks, right? So VB minus VA equal to what? 12 divided by 0.01, which is nothing but 1200. This is nothing but 1200 volts. Okay, so I hope this concept is also pretty much clear for you. The concept based on what? Work done by external force and work done by the electric force. So this is basically work done by conservative force, which you would have already learned in Newton's laws, right? In the mechanics part, you would have learned that work done by conservative force is nothing but what? Minus change in potential energy. So work done by gravity and all those things, right? So work done by external force is given as what? The change in potential energy. Fine, so that is also clear. So now let us move on to the next question. So in this question they are telling electric field of 20 Newton per coulomb exists along x-axis. They are telling that there is a field along x-axis and they are asking us to find the potential. So they are asking us to find the potential difference between what? B and A, VB minus VA they are asking, and they have given us 3 cases to solve, right? So this is the let's say case A, I'm just drawing the coordinate axis over here. Let's say this is y axis and let's say this is x axis. So So this is very very important. And when they say the electric field is along x-axis, see here it's very very important. As I said, one of the favorite concept for like competitive exams to give question from is what? Uniform electric field, right? So you need to understand that magnitude is fixed and direction is also fixed. Both magnitude and direction are fixed, right? So as both magnitude and direction are fixed, the given field is what? The key important part. As both magnitude and direction is fixed, that is given field is what? That is given field is a uniform field. Given field is uniform field. Whatever the field that they have given, so that field is what? Uniform field. Whenever uniform field is there, you can use the formula that I already told, right? So okay, fine. So here they are asking us to find the potential difference between what? 0, 0 and 4, 2. So that means 0, 0 will be something over here and 4, 2 will be something over here, right? B would be where? Something over here. So this will be our 4, 2. So this is our B. See, try to understand this concept very carefully. It's an important question. So this is 4, 2. And this is our B point. So you need to understand that as the electric field lines are only along x-axis, you need to understand that the potential drop will be there only along x-axis. There won't be any potential drop in what direction? Y direction. Why? Because so it's a uniform electric field. So in the case of uniform electric field, potential drop will be there only in the direction of electric field, as there is no component. When it is uniform, when I say field is uniform, tell me, is there any component of electric field in vertical direction? Obviously there is no way that we can have a component of electric field in what? Vertical direction. When there is no way that we can have a like electric field in vertical direction, that means so when there is no electric field, so when what is the reason for having no electric field? Obviously the potentials must be same, because if the potentials are different, immediately there exists an electric field line between those 2 points. So when there is no electric field component perpendicular to the like field direction in case of uniform electric field, that means you need to understand that as there is no field, that means there shouldn't be any potential difference. So that means the potential of A, and you guys need to understand, I am keeping a new point here. So the potential of A and potential of C must be what? Same. And the distance between A and C is nothing but what? 4 now. So now you guys need to understand, as I said, VB equal to what? VC. VB equal to VC. So very clearly explain why VB equal to VC. Why? Because in a uniform electric field, it's already along what direction? The given field is in along x direction, right? Given field is in what direction? Electric field is in x direction. So as it is uniform electric field in x direction, there won't be any potential change in what direction? Direction which is perpendicular to that. That might be a y or that might be z. So complete both y and z will be an equipotential surface. So that's why you'll be getting a plane. Okay, so here the locus of all the points which will be having equipotential will form a plane. So that plane we'll call it as like what's our equipotential surfaces. Okay, that's a different concept. So you understood why VB equal to VC, because there is no electric field in this direction. Now I can find VA minus VC. Sir, how I can find VA minus VC? VA minus VC you can easily find by using the formula. Delta V magnitude is nothing but what? We know delta V magnitude is nothing but what? E multiplied by delta R. E multiplied by delta R. Okay, this is the magnitude. So E electric field already is given as what? 20, and delta R is what? 480. So 20 into 4, which is equal to 80. But you guys need to understand which potential is more. Electric field lines will always flow from higher to lower potential, right? That means you need to tell delta V is nothing but what? VA minus VC. So here I am just writing the magnitudes. Okay, don't confuse. Don't think that sir you have left the minus sign. Always I'll write the like magnitudes, and I'll take the change by using the concept of like electric field lines will only flow from higher potential to lower potential. Okay, that part you shouldn't confuse. I'm taking the magnitude and in calculating involving the direction sign. So ensuring that what? Already as I know that electric field lines can flow only from higher potential to lower potential. As I know VB equal to VC, now VC can be replaced with what? VB. So therefore VA minus VB equal to what? VA minus VB equal to 80. but they're asking VB minus VA, so the answer would be what? Minus 80 for the first case. Minus 80 for the first case, right? So in the second for the B part, so let us analyze what they're asking for the B part. So in the B part, they're asking the 2 points that they have given are what? 4 comma 2 and 6 comma 5. So let us try to analyze this one also. So if you understood the case A and case B and case C, you can easily solve. So where the first charge is 4 comma 2, 4 comma 2. This is our A, 4 comma 2. And the another charge is at where 6 comma 5, 6 comma 5. So this is our charge A and this is our charge B. This is our charge A and this is our charge B. So now what you should do, like I'll just drop a perpendicular line onto the x-axis. Let me take this point as C and let me take this point as what? D, and separation between the points C and D. Separation between the points C and D is nothing but what? 2. Right? 4 and 2. Along x-axis 4, along x-axis 2. Now instead of doing all these things, okay, I'll just directly use the formula that I already told. So you need to take for finding delta V. Okay, so you just need to take the delta R, the distance along the field directions, right? So you just need to take the delta R along the field direction. You need to understand this is not along the field direction. Along the field direction means what? Along the field direction means horizontal direction. Along the field means what? Along the field means what direction? Horizontal direction. Horizontal direction. Along the field means horizontal direction. Okay, so horizontal direction. So if it is in horizontal direction, simply I can find the value of delta V. Therefore delta V, potential difference, is nothing but magnitude. E, electric field, is already given. E into delta R. E into delta R I will write. E is given as what? E is given as 20 and delta R in this case is what? 2. So therefore, but which will be at the higher potential? Obviously field lines are going right side. That means C will be more potential than what? D. So if C is more than D, so C and A should have same potential and D and B should have same potential. So therefore here also again VA minus VB would be equal to what? 40 volts. So if they are asking VB minus VA, obviously the answer would be what? Minus 40. Okay. So I'm not going to do the third part. Okay, you guys can approach from you can find it over there. And they're asking what is the conclusion, right? The conclusion would be C. So they have given first O to A to B, and then basically B to C. If you just try to ensure adding all these things, as it will form a cyclic loop, that means let's say from here to here and then here to here and then here to here. As we know, electric field is a conservative one. Work done in any closed path would be what? 0. So if you add all the potentials in proper manner, that means in a cyclic way, that means VA minus VB and then O to A, B to C and C to A, then the sum of all the potential difference would be what? 0. So why the sum of all the potential difference would be 0? Why? Because as I said, electric field is an what? Conservative one. Work done in any closed path, doesn't matter. Okay, it's whatever the path is, even if it's a random path, if you are coming back to the same point, so work done should be what? 0. So that means if I take Q outside, work done is nothing but change in potential energy. If I take charge outside, that means sum of all the potential drops must be equal to 0 in any closed path case. Okay, I hope it is clear. It's an important one. C part you guys can try and check whether whatever the note point that I've said, it's getting validated or not. Okay, fine sir. In the next case, an electric field E bar so and so is given, exists in the space. The potential at the origin is given, and then they are asking what's the potential at this point. So these type of questions, an electric field is given in vector form. When electric field is given in vector form, then remember you need to approach by using this method. So whenever electric field is given in vector form, then remember delta V is given as minus integral E bar dot dr bar, right? Basically E is actually minus dV by dr, so I'll take it dV also. I'll just tell how we got this. So already you know E is nothing but what? Minus dV by dr. So from here you will be getting actually minus dV equal to how much you are going to get? EdR. Okay, but when I do integral, so then integral dV, which is nothing but minus integral EdR. But when electric field is given in a vector form, then you need to understand that it should be written as what? Instead of simply writing EDR, you need to write E bar dot dr bar, E bar dot dr bar. So integral dv is nothing but what? Delta v. So delta v is nothing but minus integral electric field is given in a form of what? Vector. So whenever electric field is given in form of vector, so that is 20 I cap plus 30 j cap. Remember dr bar should also be written as what? In vector form. So that is dx I cap. The small displacement dr bar can be written as what? Dx I cap plus dy j cap. Dx I cap plus dy j cap. If z is also there, if z component is also given, then I'll write dz k cap. Then I'll write what? Dz k cap. So then from here you guys can integrate it, right? So when you integrate it, simply what will you get? So minus, so you need to do dot product, right? When you do dot product, so similar term should be multiplied. That means integral 20 dx and minus integral 30 dy. So it is taken from which point to which point? So you need to understand that delta v. So let me write it as v and keep the limits from where to where, origin, that is 0, 0 to 2, 2. That means origin to the point P. Let me consider that this is origin. This is origin and this is point P. And this is x is taken from where? 0 to 2. Origin means 0 and P, point P is 2. Y is also taken from 0 to what? 2. So therefore Vp minus V0 which is equal to minus 20 dx is nothing but what? 20x, 0 to 2, and here also you will be getting 30y, and where to where? 0 to 2. So therefore it is 40 plus 60, it is what? 100, minus 100 you are getting, and Vp minus V0, right? Here they are telling if the potential at origin is taken to be 0. Potential at origin is taken as what? 0. Potential, if this is 0, if V is VO, potential at origin is taken as 0. So therefore what is the answer you will be getting? Potential at that point, whatever the point that they are asking, is nothing but what? Minus 100 volts. Minus 100 volts. I hope this is also pretty much clear for you. When electric field is given as vector, then this is the approach that you need to follow. Okay, and when potential is given as a function and they are asking electric field in a vector form, so that type of model is also there. That also we'll see. Basically you need to understand electric field is a vector and like potential is about scalar quantity. So whatever the formula that you guys in general remember, that is E equal to, sorry, I know the formula, E equal to minus dV by dr. This is a scalar form, right? This is a scalar form. See, remember, when both are given in scalar forms, then I'll use this formula. But when electric field is given in vector form, there are three cases. Okay, when E is given as scalar and V is given, like E magnitude, E is given as scalar, that means magnitude there I am talking about. E is not a scalar quantity, I am talking about magnitude. If I just want to bother about the magnitude of electric field and it's not given in a vector form, and then simply I'll use this formula. When V is given as a function of R, or when E is given as a function of R, I'll directly use this formula, vice versa. When E is given as R, then also I'll use this formula. R means R can be there, X can be there, Y can be there, depending on in what direction the particle is moving. And similarly, but when electric field is given in the form of vector, then remember delta V should be written as minus integral E bar dot dr bar, E bar dot what? Dr bar. But when potential is given, and you want to find the electric field in vector form. Okay, this is when potential is given and you just need to find the scalar form of electric field, then this is fine. Or else when electric field is given, basically I can write there are total 4 models that are possible. Total 4 models are possible. So that is, similarly dV is simply written as what? Minus integral EDR. So first 2 models are what? First 2 models are dealing with both scalar. Both scalars. Okay, both scalars means, like, so you need to understand my whatever my sense that is there. That is, okay, both are scalar means again you will be telling, sir, you're telling electric field is a scalar quantity. So here what I mean is if both are given as a function of some distance, function of r or function of x or function of y. So they haven't given in a vector form. Electric field is not given in vector form. And the next 2 formulas are used when electric field, either electric field is given in vector form, I'll use, or I want the electric field to be in vector form, then I'll use this. This is finding electric field and this is finding potential. This is finding potential difference when electric field is given as a vector form, and this is finding electric field, this is finding electric field when potential is given as a function of R. Then what is the formula you'll be having? Minus dou V by dou X I cap minus dou V by dou Y J cap. Dou means partial differentiation, minus dou V by dou Z, minus dou V by dou Z K cap, minus dou V by dou Z K cap. So these are the 4 different models that are possible. Okay, so based on these 4 models I can create n number of questions, and you will be seeing plenty number of models based on this concept whatever I have explained over here, whatever the concepts. Okay, so the first 2 are finding E when V is given as a function of R, or finding delta V, okay, finding delta V. This integral dV is nothing but delta V when E is given as a function of what? E is given as a function of R. And the next 2 is when electric field is given as a vector, how to find the potential difference, and when potential is given as a function, some variables, how to find electric field in the form of vector. So basically four models only you will be able to find based on relation between E and V. So this is basically the summary of finding relation between E and V and the different models that you guys can see based on relation between E and V. Okay, so I hope it is clear, pretty much clear for you. So then coming to this question, so here electric field is given as what? Some AXI cap. That means you need to understand it's a non-uniform electric field. Sir, how you are telling it's a non-uniform electric field? Obviously because this electric field is changing its magnitude with respect to what? With the distance, right? So along with this distance x, the electric field is magnitude, strength is changing. So when the strength is changing, then we won't call it as what? Uniform electric field. So then they're asking about potential only, right? But now it is given in vector form, but no need of bothering vectors, simply its direction. Its direction is in along what? X-axis. So basically directly I can write the formula as what? The potential difference only they are asking, right? So again E equal to, simply I'll write what? Minus dV by dr. So instead of dV by dr, now the motion is along x-axis, so simply directly I took minus dV by dx. That means dV equal to what? Minus E dx, and I'll do integrating on both the sides. So integral dV is what? V, and minus integral E, I'll replace it what? E, I'll replace it with ax into what? Dx. And the limits of potential from where to where I'll take. So here they're telling from this point, let's say point P to origin we are taking. From point P to origin we are taking. So that means point P x coordinate is where? Point, we should only bother about x coordinate. Y coordinate doesn't matter for us because here there is no y term here, right? So there is no like y component here in the electric field. So x component is changing from when it is at a point P, x coordinate is what? 10, and when it is at origin, the x coordinate will be what? 0. So therefore the potential at O minus potential at P will be equal to minus ax square by 2 minus ax square by 2. Limits are from where to where? 10 to 0. Limits are from where to where? 10 to 0. So because of this minus sign, the like these things will be like what? Instead of writing upper limit minus lower limit, I'll write lower limit minus upper limit. And clearly they told potential at P. Okay, the potential at this point is assumed or like considered to be what? 0. That's what they're asking. So therefore potential at the origin, VO is nothing but, so as I said, because of the minus, the limits will be changed. A by 2 is nothing but what? A by 2 is 10 by 2 is 5, and upper limit 100 minus 0 is nothing but what? 100. So the answer is what? Potential at the origin will be equal to what? 500 volts. So the potential at origin will be equal to what? 500 volts. So I hope this is also pretty much clear for you, right? And this is the final model that I have told in case of what? Relation between E and V. When V is given as a function of xyz, they are asking you to find what? Electric field. They are asking you to find the expression for what? Electric field. So the magnitude, like once you find the expression for electric field, so automatically you guys can solve all these things. So dimensional formula and all I'm not doing. Okay, so I'm just focusing on the electric potential this chapter only. Okay, so as I said, so the electric field simply electric field E bar can be written as what? Minus dou. Dou means partial differentiation. What is partial differentiation? Let us understand over here. So dou V by dou X I cap minus dou V by dou Y J cap minus dou V by dou Z K cap minus dou V by dou Z K cap. Okay, so then, so what is the meaning of dou V by dou X? You know, what is the value of V they have given? The value of V that they have given is V of X comma Y comma Z. They have given A XY plus YZ plus ZX. So then from here, let me write dou V by dou X. Dou V by dou X means, so in the whatever the function that is given, you need to consider only X as variable and remaining all things are constants. Only X is variable and remaining all things are constants. Okay, so by considering that only X is variable, so differentiation of X is what? Differentiation of XY is what? Simply Y, and differentiation of YZ is what? 0. Differentiation of XZ is what? Z. So therefore dou V by dou X is nothing but what? A of Y plus Z. So this is a dou V by dou X. Similarly dou V by dou Y, which is equal to A into, when you are differentiating with respect to Y, you will be getting X, you will be getting Z, and there is no Y term in the final thing, so you will be getting 0. So therefore A of what? A of X plus Z, and final term that you need to find is what? Final term that you need to find is dou V by dou Z, so that is, so in XY term there is no Z, so you will be getting differentiation as 0, and in YZ you will be getting Y, and then XZ you will be getting it as what? X. So therefore A of what? A of X plus Y, A of X plus Y. So since I got all these values, I'll just substitute over here and I'll be able to get the electric field, so in a vector form. Let's say they're asking what is the magnitude of electric field at this point. Just substitute 1 in all these things and you'll be getting something I cap plus something j cap plus something k cap. So magnitude is nothing but under root of x component square plus y component square plus z component square. You will be getting the magnetic field at whatever the point that they are asking. So this is the final model that I have told in case of what? Relation between E and V. Right? So I hope this is also very clear for you, and it's a very, very important model. And coming to this question, two charged particles having so and so brought from infinity to within a separation of 10 centimeters, the increase in electric potential energy is nothing but, see, when they are at infinite separation, V initial, U initial, potential energy initial will be equal to what? K Q1 Q2 by initial separation is infinite, so which is nothing but what? 0. Initial interaction energy will be what? 0. Now the final this is initial, and final potential energy would be what? Simply K Q1 Q2 by, they are asking final increase in potential energy only. No, initial potential energy will be anyway 0 because they are telling that they are brought from infinity. So simply K Q1 Q2 by R. So just substitute the values of these charges, Q value and R value with proper units, and you're going to get the answer. It's a straightforward one, right? And this is very, very important one. Okay, so this is a question based on what? Equipotential surfaces. What are equipotential surface? The locus of all the points which are having same potential. The locus of all the points which are having same potentials is called as what? Equipotential surface. So when potentials are given like this, so you can understand that, you can see that from here to here all the points have same potential, from here to here all the points got equipotential. So that means when I draw these lines like this, the first one I am doing, when I draw this like this, they are parallel, right? So parallel like this, and you need to understand that the potential throughout this line is same, right? As the potential throughout that line is same, that means no electric field is going to be there along this direction. That means you guys need to understand that there is only one way that the electric fields can exist. So how the electric fields can exist? Remember, whenever we have planar kind of potential, like plane surfaces, okay, plane equipotential surfaces, that means you need to understand that the electric field is what? Uniform electric field. For what type of electric field you will be getting plane equipotential surfaces? Uniform electric field. For what you are going to get spherical equipotential surfaces? For point charge. Okay, so that point I'll write. So that means you need to understand that field can only be there from here, like in this direction, right? So now let me just do the geometry over here and figure it out what will be the answer. So as I said, electric field will be there from here to here only. This length will be equal to, sorry, this potential difference delta V in this case simply is given as what, 10. So between each two lines the difference is what, 10. And you can see that the distance between any two horizontal lines, the distance between like any two these parallel lines, horizontal distance is known. Horizontal distance means I know this distance basically. What distance I know? I know this distance. But what distance I need to find? I know the delta R in the formula delta V equal to E delta R. I need to find delta R which is, okay, which is in the direction of what? So don't get confused, this is not separation, this is the potential difference. Let me write here, this is 10 volt, this is 20 volt, and this is 30 volt. So obviously the electric field will go from higher potential to lower potential. So therefore the field lines would be going like this. So how the field lines would be there? Like this. And as I said, we need to take delta R bar in the direction of field. That means what is the thing we need to find, you know? This is the value we need to find. This is the value. This is our delta R. This is the distance, delta R. So how to find this delta R? So this horizontal distance separation between them is given as 10 centimeters, which is nothing but 0.1. And it is making an angle 30 degrees with the horizontal. So as this, so this given is that this line is making how much angle with the horizontal? 30 degrees. So obviously this line, so these are like alternate angles, so this angle will also be 30. So from this right angle triangle, tan 30 is nothing but what? Tan 30 degrees is nothing but opposite side delta R, which is in the direction of field, along the direction of field, by what is the value, the other distance, adjacent side, my bad, so that is sin 30. Opposite side and hypotenuse I know, right? So I need to apply sin 30. Sin 30 equal to opposite side delta R by hypotenuse 0.1. So which implies delta R equal to 0.1 divided by sin 30 is what? 1 by 2. So this is the value of delta R. Once I get the value of delta R, the electric field I want to find, right? So electric field is nothing but delta V by delta R in the direction of electric field. Potential difference is what? 10, and this delta R is nothing but what? 0.1 divided by 2. 0.1 divided by 2, which is nothing but 20 by 0.1, which is nothing but what? 200 Newton meter. 200 sorry, so I can tell 200 volt per meter, or like Newton per coulomb, okay, or Newton per coulomb. So this is the value of electric field, okay, and you're going to get what kind of electric field? Uniform electric field you will be getting. You will be getting uniform electric field. Okay, so in case of planar equipotential surface, what type of electric field you are going to get? Uniform electric field you are going to get. Okay, so fine, that's done. The next question is also very important one. So here, to solve this question, you need to find the relation between like the potential and distance R. You need to check for the speciality here. The speciality is 10. At a 10 distance R, the potential is what? 60. And at a distance of 20 centimeters, it is what? 30 volts. And at a distance of 30 centimeters, that is 0.3 meters, the potential is what? 20. So if you just multiply V and R, so you are getting VR equal to what? So you need to understand VR, you are getting it as constant. VR, we are getting it as constant. What is that constant value? That 0.1 into 60. 0.1 into 60, you are getting 6. VR, you are getting it as what? 6. Then, so what is the value of VR you are getting? VR equal to 6. VR equal to 6. That means V is nothing but what? 6 by R. Then what is the value of electric field? Electric field is nothing but what? Minus dV by dr. Minus dV by dr. So therefore what will you get? Minus 6 by r square. Minus 6 by r square. 1 by r differentiation is what? Minus 1 by r square. So here minus indicates that the field will be there in the direction of field only. So if I just ask you to find what is the magnitude of electric field, the magnitude of electric field is nothing but what? Simply. Or else the dV, actually the dV sign would be what? dV sign would be negative. Why? Because if I am going in the direction of like electric field like this in r bar direction, Okay, and if I go in r bar direction, the change delta v will be what? Delta v would be negative. Okay, so I'm just telling you how we got that value as positive only. It's just a magnitude. Okay, if you're getting, anytime you're getting confused with the like sign, right, you just take the magnitude. As I said, never get confused with the sign. You just take always the positive value, and from there you need to understand that field will always go from higher potential to lower potential. So here this is higher to lower, so the field lines will go like this. Okay, but in the why we are getting a negative value here means the dv value, why it is negative means in the r bar direction, that means as I increase the distance in the r bar direction, the potential is what? Decreasing. So when it is decreasing, if I do final minus initial, obviously I'll get negative, right? So whenever something is decreasing, the rate will be negative. So that's why here we will be having a negative sign here, indicating the direction. Okay, so I hope it's clear. So the magnitude is what? 6 by r square, and the direction will be like, what's the direction? Is radial direction. Direction is what? Direction is radial, radially outward, So why? Because the potential is decreasing in that manner only. No, potential is decreasing in that manner. So therefore the field lines will be like, what's that? The magnitude is 6 by r square. Okay, 6 by r square, and the direction is what? And the direction is radially outward. Okay, so I hope this is also clear. But I told I'll be telling an important concept here also, right? Important note point, that is like type of field and type of situation and equipotential surface. What situation is there? And locus of EP points means equipotential points. Locus of equipotential points. So in the first case, I'll be taking situation of uniform electric field. First case I'll take it as what? Uniform E bar. Okay, when you take uniform electric field, what type of like equipotential points you're going to get? What type of equipotential surface you're going to get? Planar surface you're going to get. What you're going to get? Planar surface. And if the situation that is given, if the situation that is given is a point charge, and for a point charge, okay, you know what type of surface you are going to get? Equipotential surface. Why? Because whenever a point charge is given, so the potential at a given distance are anywhere irrespective of the direction. So the potential formula is given as what? Kq by r. So locus of all the points which are equidistant from a point is nothing but a what? Sphere. So that's why here what you will be getting? Spherical surfaces. What will you get? Spherical surfaces. When you have point charge, you are going to get what? You're going to get spherical surfaces. And what about the third one? If we have a line charge, if we have a what? Line charge or linear charge? Line charge. When you have a line charge, then the locus of the points which will have the same potential is nothing but what? Cylindrical. You'll be having cylindrical surfaces. You'll be having what? Cylindrical surfaces. Okay, so I hope this concept is pretty much clear for you. And coming to the next question, so here they're asking what's the work done in assembling all these things. So this one already we have found, right? In the last class already we have solved this. Okay, yeah, so that's all. So we have completed so this is very important concept. Okay, so this is very important concept, so of equipotential surface, and these two are like pretty much standard examples that you can see in the exams and like in different books as well. Okay, so I hope it's pretty much clear for you guys. So I have tried to complete all the questions and all the models that is given in HC Verma. So theory part already I have completed, and I left out two theory parts, right? That is like relation between E and V, so that I have extensively discussed over here. Okay, so what are the different types of models that they can be asked, right? Here I have clearly discussed here. Okay, what are the different models that they can arise from the relation between E and V. Okay, so just by solving some models you will be having a clear idea. Okay, just by solving some important models and what are the standard books that you will find, by solving you will be getting an idea. So this is the concept that I have left out. And as I said, one more important concept that I left out is what? Equipotential surfaces. That also very clearly I have explained by taking the standard question that is given in HC Verma and giving you all the different cases and different scenarios that are there. Okay, so I hope it's clear for you, pretty much clear for you. Once again, just go through all the questions whatever I explained. So you need to understand that here our, like, my motive is not just solving the questions, right? So I am trying to, like, inculcate the ideas or the, like, process, the path in which you need to approach a question, how to, like, understand each and every key point. Okay, like key point in that particular concept, whatever that is there. So I hope it's clear for everyone, all of you. So thank you guys, bye bye.